I'm Ken Birman. I'm a faculty member in computer science. I've been here since 1982. I've been in dialogue with the systems engineering field about joining the graduate field of systems engineering. I've been interested in broadening the kinds of students joining my group. And my understanding is that this type of a lunch talk is part of the process of vetting potential new systems engineering field members. So that's our purpose today. A little about myself. I work in distributed systems and have actually since I joined Cornell. My broader area would fall into what you would call operating systems, cloud computing. Students of mine have helped create some of the very big cloud infrastructures. For example, Werner Vogels, who got a PhD partly under my supervision. It was actually awarded from the Netherlands. He's the chief technology officer at Amazon these days. Ranveer Chandra is another PhD of mine. He's chief scientist for Microsoft's cloud computing infrastructure. And I could make a much longer list actually. So my students often go on to contribute in these very big infrastructures. I've also done companies along the way. We built the software that has run the French air traffic control system since 1996 without a problem for that entire time. It's about time they moved on to something else actually and migrated out. I also wrote the software that ran the floor of the New York Stock Exchange, the trading system down there, and was in use for more than a decade before it was eventually replaced. Swiss Stock Exchange, many VLSI fab factories, and more recently I've done a lot of work with electric power grid. And I'm a member of IEEE fellows, and I'm an ACM fellow as well. So that's a little bit about me. Active in the field and continue to be active. What I want to tell you about today is work in progress, a new system that we're currently developing called Cascade. It's layered over an older system that is open source, which we developed and released successfully. It has relatively few users. I'll say something about that later. But we're very excited about it, and Cascade seeks to take the Dracho work into the machine learning kind of environment, particularly for Internet of Things. And so the kind of application that motivates us, this is some work that Microsoft actually urged us to do with Cascade, and it's currently one of our big targets is to demonstrate something like this. They give us funding to do so. Imagine that you have satellites which are overflying agricultural regions, and you wanted to take the satellite imagery, ignore it if it has clouds, because you don't want to pay for data that you're not actually interested in. But if it's a nice clean shot like this, you might want to set particular spectral settings on the satellite, have kind of a dialogue with it, and perhaps combine that information with river flood levels. You see there's a river running through this picture, and water hydration levels in your fields in order to arrive at intelligence that you might communicate to your users. For example, the farmer should plant certain crops or graze the cattle in a certain field, or perhaps maybe just leave it fallow because it's going to be flooded all summer. Now, if you think about these kinds of applications, they typically result in what we would call a network of AI agents, where you have different computing agents that are machine learning components, entire recognizers, classifiers. They could be machine learning training systems. They're trying to learn the hydration level, or they could be looking at weather and making predictions about river flood stages 3 months out. And so each of these little circles in the graph I've drawn is intended to be a separate machine learning component that somebody built. More and more, we're starting to see machine learning systems where these systems are composed together. So you have multiple expert systems that talk to each other and produce a kind of a graphical structure where input flows in at the left, and then it might propagate through. So for example, new data from the satellite could cause you to update your predictions about which fields might be at risk of flooding, which could cause you to upgrade your recommendations to the farmer, which could cause an insurance company to change its estimates about actuarial risk in that region, for example. And so this kind of a picture is becoming more and more dominant. The icon I've got up in the top right corner is actually from Microsoft. Instead of little circles, they put what are called Lambda notations in them. They're trying to express the idea that the developer provides some code that customizes an existing framework. Code takes the form of a function, and in computer science, we often refer to that type of a plug-in function as a lambda. And so the idea is supposed to be shown here, this little brain, that the developer has created a graph of plugged in functions in a cloud that carry out some sort of intelligence. This one is supposed to be illustrating what's called industrial IoT, where you perhaps are doing things like 3D visualization in real time, what they call augmented reality. You can imagine a car repair mechanic who's directed to the carburetor and sees a visualization of how to unhook this particular kind of carburetor to fix something. So that's what this picture is supposed to be showing. And that's the type of thing people are interested in doing these days. 5G, the new telephony technology, is going to push this much further. But I'm already talking to people who are doing this type of work in robotics. I'll tell you about smart farming, in smart homes. One of our colleagues from a couple of years ago, Ashutosh Saxena, has a company doing smart homes for the elderly. And a very, very successful one. And then there's an entire emerging area called digital twin technologies, where the cloud tries to have a digital representation corresponding to a physical infrastructure, like the electric power grid. I do a lot of work with smart power grid people. And what you do is you have a digital twin of the smart power grid. The smartness is actually in the cloud. The integration with the physical version involves connecting to sensors and actuators that give you control points, and then you're able to operate on the digital twin version and cause an effect in the real world. So these applications form a graph and graphical collection of components, and the different components could use all sorts of different AI technologies. Each one represents a computational task that might actually be parallel over multiple machines. And we're trying to arrange for real-time data flow between different tasks. And as I said, the Lambda is just a notation for suggesting that you took a general purpose AI engine and customized it for your purpose by plugging in specialist functions that relate to knowledge about your particular kind of data. This Lambda notation is popular these days. And in fact, the idea of building cloud solutions by customizing existing platforms is very common. I teach cloud computing right now, and we have the challenge actually of teaching people that they're not building from the ground up, that the smart way to get a scalable solution in the cloud is to customize something that scales and turn it into a specialist for your application, but not rebuild the whole infrastructure. It's just too hard to get scalable solutions that really are robust. I teach people how to do it, but it takes years of development to get them right. So you're generally customizing these platforms and trying to plug them together to get this. Now, the irony is that although this is the prevailing model and you're actually seeing icons like the one for Microsoft, as a matter of fact, today's cloud platforms are a pretty poor match to this kind of use case. They don't have the right real-time characteristics or data consistency guarantees that are needed when you start to deal with a physical world like a power grid. And as a result, people who have been trying to build these kinds of solutions are investing a great deal of effort. They're finding obstacles left and right, that the cloud just isn't oriented around that. It's just surprising because the cloud is where you do AI these days, but it's oriented around a kind of AI where the ingress of data tends to be file uploads. It may be days or months or something before you actually run a machine learning training application. By the time you do, you've aggregated a huge batch of work to do, and then they're optimized around this kind of offline batch style of computing using infrastructures you've probably heard of, like MapReduce. And trying to do this in real time is not something that is common at all. So the goals of this new project, Cascade, the two leaders are myself and my postdoc, Weijia Song, who actually now is a full-time permanent employee, so I'm a research associate, are to create a real-time infrastructure that integrates well with today's existing cloud so that you could imagine deploying it in Amazon or Google or Microsoft. So Cascade is going to be an open source Cornell developed research artifact, Air Force supported actually, but that's intended to be used in those kinds of settings. Very easy to use so that people who are already working with some existing technology for machine learning can port their code with minimal effort. but that magically brings them real-time responsiveness and scalability and consistency in this new kind of environment. So, in order to understand our goals more deeply, a big question that would arise is to understand how today's machine learning platforms work. And what's notable about them is that they don't just work, they're actually highly effective. They're not designed for the IoT real-time environment, but they achieve extremely high utilization levels for the hardware and are really very popular for that reason. And so it's important to realize that if we're going to ask people to port machine learning logic that they've created elsewhere into this new operating system, if you want to call it that, for the edge, our system had better support their style of code. So what you find if you look inside is that machine learning program systems are massively parallel. In fact, they have a lot in common with high performance computing on supercomputers. However, whereas HPC platforms often use the supercomputer in a kind of semi-synchronous way, where you might take 1,000 computing nodes and compute in a kind of coordinated manner, where the nodes talk to each other using a platform like MPI, the message passing interface, would become widely standard in HPC. In cloud settings, you actually find that the machine learning code is massively parallel and involves large numbers of independent tasks that periodically mix their outputs, but where the actual work is mostly done independently. So you may have a single node with a GPU, and it's doing some piece of work, and there's another node, another piece of work, and there are 1,000 like that. And then at the end of that stage, they combine their partial results. There's some kind of a parameter server that combines these results, and then it outputs the next set of tasks to do. And even that parameter server itself could be a parallel entity. And so you're seeing a situation where we spread our data out. And in fact, the reason people favor the cloud is because it's more cost effective to use the cloud than an HPC system. The cloud is a very good environment for independent pieces of work that can be done kind of locally on one machine. The machine can be kind of a mini supercomputer, but you don't have to worry about the bulk synchronized behavior. And so these machines can be scheduled in a shared way, and there are other kinds of cost advantages that accrue. Whereas the HPC supercomputer tends to be dedicated to one user at a time for some group of nodes. So the modern cloud is cheaper. It's much more cheap, as long as it's being used cost effectively. And so all these kinds of platforms you've undoubtedly heard of run in this kind of an environment. And what's interesting to realize is that the way that they interact with the cloud, the operating system they presume, is what's called a sharded file system representation, where data is actually spread out across a large number of servers, and then the cloud computation is spread out over a lot of compute nodes. And this allows a kind of parallel and independent interaction between any given compute node and some piece of the file system, with the effect that you get high scaling. And then the whole style of computing, favored by, say, MapReduce, or the more modern versions would be Hadoop and Databricks, or some of the other languages I mentioned, they start there, and then they go further and think about scheduling and so forth. So how does this kind of sharding work? It's almost trivial, actually. You take the name of your input objects, which are files probably, some sort of name, and you use a software system to hash that into a number in a predictable, deterministic way. So I take a string and I suddenly have a 64-bit number. I think of this number as a key identifying a value. The value is just the byte vector in the file. Could be small, could be gigantic. That doesn't really change things. Now my idea is going to be to place the file, this kind of key value tuple, on some server in a pool of S servers. And the server that's responsible for this file is considered to be a shard of the overall aggregated data space. So you imagine you have a gigantic database, you smash it into pieces, and one of the pieces has some of the data, and that's the model. You can make this a fault-tolerant shard by replicating the members. It's often done. Get a little load balancing as well. But the basic idea has become very standard. These are called key value or distributed hash table architectures. And file systems for the modern cloud always use this approach. And the reason I've been explaining all of this is because in order for us to introduce Cascade into this environment, the place to start is to replace the storage system with a new storage system with better real-time characteristics. Now, a second observation about today's cloud is that it's a very batch-oriented environment, and that this is why it's pretty bad for real time. So by batching, I simply mean that the style of computing that's emerged collects a large number of small tasks and then has an optimization approach aimed at doing lots of small tasks in parallel as part of one job. So you batched up the small tasks, but they had to wait because obviously if your events are flowing in one by one, that's not a batch. And so if you want to have 10,000 events or 1,000,000 events in a batch, well, the first event is going to wait till the other, 9,999 have accumulated, and that's going to take time. And so what you find is that it's not a very good real-time environment. What's usually done is you use the batch layer of the cloud to train machine learning models, which is a slow task. And then you might take the model you've ended up with and put what are called the classifiers, which use the model closer to the IoT edge. And so for example, if you were asking about how does advertising placement work in today's cloud, you'd find that the ad placement models are trained in a batch style offline, but used in a more online style. And the computations that use the models are somewhat cheaper and can be spread out at the edge. It's still not all that great for real-time purposes, but that's how the cloud works. The trouble with IoT is that the contextual information that you're going to be using when you manage a smart home or a smart power grid or a smart city in some way, it needs to be very, very fresh data. You don't want to manage a smart highway by telling the cars that, oh, it's okay to change lanes at a moment when the lane is actually quite occupied because the car is coming up fast. So that type of staleness would cause problems. It turns out that type of staleness is tolerated in today's web systems. And so we have the difficulty that if you took today's batch style systems, it's really pretty poor from a real-time perspective. And if you tried to push them hard, you become extremely aware of the staleness phenomenon, which they embrace actually, and you would realize it's just not going to work for you. So that's what Cascade is about. It's a project that aims at this modern style of machine learning. We want to create a new operating system for them. It's going to reside close to the IoT devices. And we're going to do this in a way that looks as friendly and familiar as possible. So our operating system API is a similar kind, not necessarily a clone, but let's say it's extremely similar to the backend systems. We're going to build a real artifact and we're going to have people really use it. My group, ever since I came to Cornell, has always built systems that people use. So we can talk now about Cascade more concretely. It's intended to be a service that runs on a cluster of computers. It could have thousands of machines available to it. And you might rent those from a cloud, so it could be used in a cloud environment. It's built over a layer called Dracho. I'll tell you a little bit about that in a few minutes. Dracho is a C++ software library, meaning that it doesn't do anything by itself. It's intended as a framework used by an infrastructure. And in this case, Cascade itself will be the user of the Dracho infrastructure library. So we're using our own software library to build our next system. Dracho is designed for ultra-fast infrastructure management and data replication. And I'll show you that. And in fact, Cascade then takes that, turns that into a sharded storage infrastructure, supports access to high-speed devices. Some of them include modern remote direct memory access devices, RDMA, GPU devices, FPGAs, modern memories like NVMe. And our idea is to create an infrastructure in which your application ports easily because it looks like what you're familiar with, benefits from these modern accelerators, which I should admit emerged from the back end and they're already pretty compatible, and then achieves very low latency as our first objective and high utilization of the hardware as a secondary objective, whereas in the batched environments, high utilization is the first objective and low latency hasn't been a goal at all. Cascade's an extensible service, and I'm going to show you what I mean by that, but fundamentally what I mean is that the user brings software that's sort of plugged in like those Lambdas, and Cascade gets customized and becomes a smart service. So for example, One of the applications I'll tell you about in a minute is a smart farm that we're doing here at Cornell with Professor Julio Giordano, who's in the vet school and CAL's unit. And Julio, he is working on high technology used in dairy farming. It's a surprisingly sophisticated undertaking. These people know machine learning inside out. However, they've been struggling with the fact that you can't connect their kind of dairy farm to a cloud and get what you want working. So Julio would like services that do things like this. Which cow am I looking at? You would think that it would be obvious from RFID, but if you've got 500 cows milling around in a gigantic lot and you're trying to find one of them because the vet is here and needs to work with this cow for some reason, where is she? That can be quite a time-consuming activity. Is this cloud clean enough to milk? And the answer is no, she's clearly not. Does this cow over here have the illness called mastitis? She doesn't, by the way. And so these kinds of questions. And then you could scale this out, and you could even scale it out globally. And Cascade is intended to follow those paths. Similar to other cloud infrastructures, I should say, what we're doing isn't necessarily innovative in all dimensions, but we want it to be a real infrastructure created at Cornell, analogous to infrastructures created at places like Berkeley. Before I mentioned that MapReduce had given way somewhat to something called Hadoop and Spark, and now there's even a company called Databricks. We're following a similar path, although I don't know about the company part, but the idea there is to really create things that are usable at the university and have third parties able to work with them. Open source, freeware, no licensing. We always use, Cornell recommends something called Apache freeware licenses, and we use the permissive Apache license. And this is all above board, and it's correct, and there are no patents that emerge and no obstacles to third-party use. So we have a storage model. We support it in two forms. I'm going to skip kind of through some of the slides now because I don't want to go for too long. I've got about 25 minutes left in the nominal 45 minutes for this slot. So Cascade has multiple, what we call application programming interfaces, multiple ways of being viewed. One of them is that it can look just like a standard file system. A second is that it uses these distributed hash table or key value store, key value representations that I talked about. The faster is the second one. You can put an object into Cascade and get it back later. And Cascade automates most of aspects of this. In fact, using theoretically interesting methods that involve optimization. If you prefer to think of Cascade as a file system, you end up going through Linux file system APIs, which are a little bit slower, but they get translated to the same operations. We support data versioning. One of the things we've noticed about IoT is not just that you have time-critical actions, but often that the actions involve accessing the same sensor over a period of time. So for example, take a power grid. The kind of question a smart grid might ask is, why am I getting such and such an instability in the power grid, maybe some sort of a phase fluctuation, every Monday at 2 in the afternoon? And now, if it's clear enough, you'd probably say, oh, that's because Corning turns on their glass foundry right at that moment, bring more power into Corning. But what if when the wind blows strongly, a certain wind farm produces more power than you're used to, and it fluctuates in some way against the underlying 60 hertz of the power grid? It may be quite hard to figure that out. So you would like to be able to support a type of query that kind of floats along in time and says, here's an example of an instability. Have you ever seen that before? Now, I'm not a scientific computing person. I want to create the environment where that type of software could be created and used. I'm the operating system for all of this, but at the same time, I want my environment to be conducive to that type of temporal computation. So if you think about what that's going to entail, it's going to mean that they won't want to say, what's the state of the power grid? They'll want to ask, what has it looked like for the last 60 seconds? Maybe David Bindel will compute some kind of analytic signature, and then he'll want to ask, have I observed that signature in the past? And hopefully we come up with a series of past positives. And then he says, what does this correlate with? And somebody says, oh, that's almost entirely correlated with strong wind on such and such a wind farm. You see? That would be the idea. So temporal queries are going to be a big deal. And we worked that out into Cascade by saying that when IoT data comes in from a particular sensor, we can just store the current value, but we can actually keep a history. And in fact, the application can keep a kind of a version delta, as if, think about this skier where we've gotten a whole series of photos, but there's a lot of similarity, and you could use that for data compression, for example. So we support this kind of mechanism built into Cascade. This is an example of the sense in which we are similar to the existing APIs. Old code could port directly, but could probably work better if it understood that we have extended APIs in some ways. So the compute model that we end up with is the following, has a puzzle in it, which is that if you really care about delay, the other issue you find with today's cloud systems is that they compute on one kind of computer, but they store on a different kind of computer, and they talk to them over the network, which means the data gets transferred. And if you're thinking about larger things, such as machine learning, where it turns out that some of the machine learning models can be a gigabyte or more, even modern very high-speed networks, that kind of a transfer is going to be slow. So you say, well, we should do caching in a smart way. That's what Berkeley's project is. It's the Spark system. In Cascade, we've been asking ourselves the same questions, but we've also gone further and asked, well, why shouldn't we have the storage and compute elements be the same compute nodes and compute on the nodes in the hope that we can co-locate data and computation in a transparent and automated way and be able to say, well, photo of my cow came in to the right place, and I already was prepared for that, and I had cached the machine learning model and the previously learned parameters for it and the hyperparameters. And so I could just compute immediately and ask if this cow is dirty or not. And that's the kind of thing that's inspired us. And again, I'm not a machine learning person, although I talk to them. I have friends who are machine learning people. And what I want to do is try to reach a point where they find a friendly infrastructure that just carries out their ideas directly. So you can get very detailed about this. As I said, I don't think I should for today's talk, but we have to ask ourselves, how are they going to express their code? What languages? How is that going to map to the key value store? This is showing a sharded key value store in which various machine learning models have been stored previously. The idea is that these shards have 3 copies each. They're just identical replicas, the round circles. The machine learning models that each shard member is holding are this sort of pile of documents. There could be many models mapped to the same shard. Right? And again, remember files. You could call them files if you prefer. This particular one's stuff you might find on a farm, like flowers and vegetables, and there'd be animals in there somewhere too. And then any one of the nodes could be asked to do a computation for you. So that's the kind of picture I'm going to show you in a minute. And then the idea will be that when you put something into Cascade, it can trigger actions which are intelligent actions. And so one of the ways that we're extending this key value model is by arranging that the act of simply storing a new value from an IoT sensor can already trigger instantly the computation required to figure out what that object is. It's interesting because we're able to keep a very, very small, thin architecture and API, and yet we seem to be able to get a very clean mapping to these IoT tasks and still preserve most of the code that ran on the back end, which is it's quite a puzzle to have so many constraints and find a path through it. So Cascade is designed to be extensible. I won't get into the details, but the idea is that the developer creates the machine learning logic that figures out if the cow is dirty or not, and gives it to us in a form similar to a compiled program. And we're going to automatically deploy that onto the Cascade nodes that are going to host the data itself. So here's our developer creating such a system, and she hands it to us. And her new piece of code, this Lambda, which might have to run on multiple nodes, it's a parallel piece of code, is going to be what we're going to register in Cascade, and we're going to put it on the same machine nodes where the hyperparameters and the trained model live, and then we're going to send in an event like a photo of a cow, and her logic is going to figure out if the cow is dirty. And then that might in turn trigger downstream actions. So if you think back to the satellite photos on the first slide, the new satellite photo came in, we could have discarded it as noise too cloudy or something. But otherwise, we might say, oh, this is useful data, and it might trigger a recomputation of our river overflow probabilities, or our estimate of how the pasture should be used in the next week or something. And each one of those could be a Lambda. So the operating system challenge in some sense is not just to support this, support it in a standard way that looks like existing things as much as possible, but also be able to instantaneously trigger these pipelines of machine learning actions. And be able to, now we're going to support any access to any object at any time, but we would like it if the object was already in the right place so that it's a zero cost. And so your optimization goal as a scheduler, for example, is to say, we're going to provide this uniform key value interface. Anything can access any object with permissions. But we would like to have placed the objects in such a way and placed the computation in such a way that it just turns out that we're always computing on the right node. So the photo came into the right place. We had everything at that place pre-positioned, and we can compute on it with no delay. And that's the really exciting vision. So here, with that same kind of a picture, would be the kind of thing you might see. Little robot, it found something awesome, it wants to know what it is, and there's maybe the first layer of a cloud. I don't know if you've had talks from Christina Delmitru in ECE. She talks a lot about these cloud microservice architectures. This is standard. They have tiers. This is called first tier. The other smart services would be what are called smart microservices, and they would sit in kind of a second tier. And so what happens, the cloud sends in a kind of a web page request, and then that gets turned into computational requests that are going to go to these sharded services where each shard has specialization. Maybe the flower model has ended up on the second shard and vegetables on the third shard. And the nodes have identical replicas for fault tolerance, but also load balancing. They figure out whether it's a good fit. It happens to be a sunflower, in fact. And so in the Lambda notation, all of the first tier is Lambda 1, all of the microservices Lambda 2. So that was what I was saying when I said earlier that the Lambdas are in a graph, right? So here there's an edge from Lambda 1 to Lambda 2, but that the Lambda itself really represents a pool of computing that might be parallel, might even be elastic in the cloud. So if we map that over to the real world, what Julio is doing, for example, is he's installed cameras on his smart dairy. One of the settings where you would like to know which cow you're looking at turns out to be when you're milking them. They're too close together and you get interference between the RFID tags. So although the cows have tags in their ears, the RFID readers are not terribly reliable. This is one of the different settings where we'd like to know which cow is which. They get muddy and then you don't get a good signal. They even tear loose sometimes. And then on the farm, you've got a little bit of compute power, but not enough. You can do thumbnails and things like that and send them to the cloud. The cloud is a very powerful environment, and that's where our smart pipeline is going to sit. And so we're actually building that right now. I should change the picture, I suppose. But anyway, we have some students who are taking software that includes images of cows, other kinds of things too. There are Fitbits for cows, temperature and other kinds of environment sensors, milk quality sensor data. We take that in, some of it ends up in tables like this data on Azure. Others are images that we don't even want to store because if the image is blurry, you might not want to store it. We had to make a promise that we would not spy on the farm workers. And part of the promise is we will not process images that have an image of any part of the farm worker visible in the image. So we have to suppress that kind of data and never store it at all. They just are worried about a big brother kind of world. And then these little lambdas, which often, you'd be surprised, the code the user provides is often quite small and often looks like database queries. So these little black boxes, these are actual lambdas. This one's written in something called PyLink, very concise, quite powerful. They include database logic and computational logic, and they can even run tests on GPUs. Images, of course, tend to want GPU work, and this would be examples that are using GPUs as accelerators to do, cow classification. The particular case tries to produce an estimate of whether the cow is going to calve soon, or if she's ready to be bred. And then you can do it in other languages. I've shown you PyLink. This is C++, but I'll just say it looks the same. So We can support lots of languages. And this style of coding, as I said earlier, is very much similar to what people are doing today in the back end of the cloud. So they should be able to port their logic easily. I wanted to show you, let's see, I want to show you an example of consistency in action. There's an entire theoretical side of what I do that's really, for me, quite exciting, but I would say secondary to building real systems. However, these are real systems that have strong specifications, and you can see the value of it right here. So this isn't a scenario that Dave Bindle suggested. It came from a power grid that we were working on. And in that kind of power grid setting, there was an issue of phase dislocations that can occur. You're capturing data from what are called synchrophasers, which are measurement units that are put on power buses in a power grid, and they give you the exact state. It's a complex angle and an exact time and a voltage, so it's like 44 bytes. And what we did was we simulated this, and this is a simulation, but oddly enough, this is a simulation where we took the simulation output and then we simulated synchrophasers in the real world, actually uploading their data in real time to a real cloud. We did this work with the New England power pool. This is ISO New England, Nightboat, which is the world's largest transmission operator, and New York State ISO, although they were not as involved, but which is ironic since we're in New York. But in any case, so you have a dislocation passing through the grid. Maybe it's coming from New York into New England. And you're imagining here a 20 by 20 grid of synchrophasers, which is not the world's most realistic thing, but that's what you're imagining. And each one of them is seeing phase angles changing as this occurs at some speed. We're passing in data at a rate of, call it 20 frames per second, 20 readings per second per sensor. So we have 400 sensors feeding data into the cloud here. And then we wrote a little visualization that just loops, but it loops taking every fourth frame. So it's going to generate this GIF is really running at 5 frames per second. And you can see it doesn't do very well on the left, right? You see all this noise. It's looping. And by the way, I should say, we could have shown you worse looking ones. This isn't even a bad one. And the reason turns out to be that the prevailing cloud file systems today, among their other features, they also assume an offline batch style of computing that has lots of time for data to settle. It's called HDFS. It's what's used. And as a result, if you try to compute very quickly after an event occurs, you see settling delays that cause you to accidentally see the prior data. Data gets mixed up in time. It's mixed up in the sense of something that Leslie Lamport formalized as causal order, and he created a concept of consistent cuts. And Cascade implements these ideas. So Cascade notion of real time is much better, as you can see in the middle. Cascade also guarantees causal cut consistency. It only actually takes us a couple of microseconds to stabilize. So HDFS plus a few microseconds of delay, and you're already over in this world. And the overheads are not high. We're actually faster, not slower than HDFS, and stronger. And on the right, we actually took our synchrophasers have synchronous GPS time. We took our data straight out of the synchrophaser. You can see how clean that is. So you can imagine if you're trying to write logic that controls a power grid, you'd much rather run on the platform on the right, my platform, Cascade, not on the left. So there's a lot more I could say. I'm going to, I think, stop on this slide. I'm going to show you how this works, and then I'm going to jump ahead to a summary. This is just to visualize why this consistency model is challenging. So remember, we sharded our data. We actually sharded over an architecture implementing a model called Paxos. I'll say a word in a moment about, this is a model created by Leslie Lamport, but Dracho, the system I built Cascade on top of that we created, has an interesting implementation of Paxos. Anyhow, so here are the shards. Time is going from top to bottom. And, we're putting data in, we're writing files if you want to use that. And then along came the events that trigger this computation, the lambdas that we've been talking about. And the data is spread over multiple shards, so the computation occurs at multiple places, and other puts are occurring. And you can imagine why HDFS has a problem now, because HDFS is running code, but when is it supposed to respond? If you say, I want the current values, what did that mean? So what we're doing in Cascade is, first of all, you're able to tell us what time you're interested in. That would be the tau over here, the time of the event epsilon. And then not only that, within that band, because the band is limited by clock precision, we're using a Leslie Lamport's consistent cut model. And that combination is what gave us the strong quality. And we have a settling delay too of a couple of microseconds, millionths of a second. And that's just illustrated here where there's fresh data that hasn't settled fully. HDFS wouldn't have noticed that and would have sometimes included it or sometimes not. Dracho just waits a little while and detects a stability guarantee and then we can reduce this to theory and we can prove the correctness of our algorithms, and then we can gain a benefit for the end user through a provably correct algorithm, which is in fact implemented and performs extremely well. So I'm going to skip this stuff. I will say a few words about Dracho. So here's the picture I was trying to give you before. So by the time we're done, you've given us logic that extended Cascade but runs on the same nodes. The photo classification request went to your logic, but in fact, it's talking to the same machine where Cascade hopefully is hosting the correct data. In fact, hopefully has cached it in the memory of the local GPU. And now the photo itself can even go directly into the GPU. And that gives us this magic combination of instantaneously computing. And then doing that on a pipeline is the big image. And then you can do these more complicated things that machine learning applications really want, or map reduce. But of course, I'm not going to talk about all these crazy arrows. Just want to give an idea that you can do all of that. All right, so Dracho, which is of course a scary term, it refers to an ultra fast straight line wind. We've had them here in Ithaca. I've actually was at a birthday party that we hosted for 8-year-olds for my daughter way back, when we noticed that the wind was blowing stuff horizontally past our house. The house was fine. It was a Dracho that had actually knocked down in a straight line every tree in front of our house, behind our house, for about 25 miles straight, like a bulldozer had just driven through the forest. Unbelievable. So our thinking is modern hardware is like that. It's very fast and very powerful. So what we did with Dracho was we implemented the layer below Cascade using these models that Leslie Lamport is famous for, state machine replication and Paxos. We rebuilt them around the idea that the model should be implemented in a way that aligns with the hardware. And interestingly, we arrived at the world's very fastest implementations of Leslie's model, far faster than anything that's out there right now. And we use that under Cascade. So this is one illustration where blue is supposed to, these are typical, this is sort of workload on particular compute nodes inside Cascade. And blue is showing work we offloaded to the hardware. In this case, it's something called RDMA hardware. And pink is work that we had to do on our compute nodes. And in a typical implementations of Leslie's kinds of algorithms, Paxos, you wouldn't see much blue. The hardware wouldn't be very busy. The host platform wouldn't actually, everybody would just be waiting all the time. It's complicated, but everyone would be waiting all the time. And your utilization of the hardware is very low, it turns out. So people haven't used this kind of consistency because they felt you can't do it efficiently. We are achieving very high hardware utilization. You can see that we have our hardware hard at work. Blue is data, in this case, being moved through our hardware. The host isn't doing much. This is the sending node. These are the receiving nodes on the right. The actual achieved performance is extraordinarily high. I mean, you can keep hardware busy stupidly, and it won't turn out that you did anything useful. In our case, we're getting a high quality of use. So this picture on the right, for example, shows Cascade or Dracho. They're the same in a sense, replicating data over varying numbers of replicas, like shards that get very big, from 2 to 16 members in this picture. For example, if we focus on the red line, what it's showing us is that if we transmitted small YouTube videos, which were about 100 megabytes, we're moving them at a data rate of 16 gigabytes per second for 2 nodes. And it's only dropping actually to around 8 gigabytes a second for 16 nodes, which would mean that to make 16 replicas, we can do the whole job from start to finish, only a small percentage slower than to make 2 replicas. It's kind of cool. And then if half of the nodes are, this red line solid is if every machine is actually transmitting video data to every other machine for some kind of parallel processing. That wouldn't really be so common. So if half of the shard members are transmitters, you get the middle red. If one of them is transmitting, but the others are workers, which would really be the more realistic case, you can see we started at around 9 gigabytes a second, and it stays at 9, roughly. And to give you some sense, the speed of the hardware is 12.5 gigabytes per second. So we actually exceed the rated speed for 2. And it's, again, very interesting that it's almost flat. You know, you can make 1 or you can make 16 copies, and it doesn't change the delay or costs at all. In fact, and this is another thing that's interesting, you see MemCopy down here? MemCopy is the way you make a copy of something in memory on a single computer. We're actually making replicas, 16 replicas, 2.5 times faster than making 1 copy in memory on the original node would have cost us. Isn't that crazy? 3.75 gigabytes a second is pretty typical for a single node making a copy. CPU has to go fetch the data, store the data. With this kind of hardware, the sender only has to fetch the data, the hardware pipelines it through, and the receiver only has to store it, and it gives us the 2.5-fold benefit. And then when we compare against prior systems with strong consistency, we're getting speed ups of hundreds or thousands of folds, which is really quite striking. People haven't wanted a C++ library, but we wanted it for Cascade. And so Cascade is going to have these kinds of speed ups compared to prior systems, hundreds or thousands of times speed ups. So I could talk about privacy, but I won't. I could talk about publications. This is just some of our recent publications on the work. The main one on Dracho is in ACM Transactions and Computer Systems. I was actually the editor there at one point for about 10 years, editor-in-chief. I was also an area editor for a few years before that. We published in other conferences, IEEE DSN, ACM Symposium on Cloud Computing, and here's this one is on ACM Transactions on Cyber Physical Systems, looks at privacy for querying smart devices. So in summary, I'll stop at this 45 minutes. We're very excited about the opportunity to move machine learning to the edge. I'm not a machine learning or supercomputing person, but I am an operating systems kind of person. And the question has been, what is the cloud missing to make that kind of very snappy IoT processing, very high efficiency so that we're using the hardware in a cost-effective way? And now we need to be offering consistency guarantees, which historically have not been the case for the cloud. And we believe with Cascade that we have that kind of a story. The work is still in progress. If you looked at this picture, these are the prior papers. We have a whole series of papers we're trying to finish up now. We have one currently pending at SIGCOMM. There are probably going to be 4 or 5 other Cascade papers on the work that I've described to you. But we really think that we've got this right, and that we're going to end up with an infrastructure that really is a quantum jump in terms of what can be done close to the IoT edge, which would mean whether you're doing the Stellarator kind of work over at the ITER fusion reactor accelerator, the project in Europe, where they have very rapid needs to control their magnets, or you're doing smart farming and you're just worried about rapidly figuring out if the cow is dirty, or if it's a smart power grid, where I've worked with folks on that kind of thing. All these different kinds of applications that glue the infrastructure to the external world, we think that there's going to just be a huge opportunity to have real impact and visibility for Cornell. Great papers for my students. And in fact, Weijia may spin something off at some point, but we're very committed that a high quality version of this be open sourced from Cornell, from my group. So with that, I'd be very happy to take questions. I know it's a round table, a virtual one, about the slides or about anything. And thank you for your attention. So I've got this participant window open. I think I'll see if people raise their hands, or you could just step in and start talking, or you can use chat if you prefer.
Hi, great talk. I was that's just so exciting to combine the aspect of machine learning and cloud. I do have a few questions. So the first question is with regard to the application performances. So normally for a user, he wants to run some machine learning algorithms, and in the hardware side, they just normally they do not have a somewhat knowledge of what kind of hardware resources they should get for the best cost efficiency and best performance. So they might, they might fetch the maximum number of GPUs available, the maximum number of memory available on the cloud. Is it? Are we doing something with regard to this?
We're trying to preserve what is standard. So if you take TensorFlow, for example, which is very popular for that type of use, in TensorFlow, there's an automated way to essentially take the cloud environment and associate TensorFlow with it so that that type of statistical information about the properties of the infrastructure is available to the application. And we can make those kinds of connections almost like a device driver for TensorFlow. So in order to take, let's say, a TensorFlow application that tried to be self-adaptive the way you're describing, and use that in Cascade, there would be the porting activity of creating the corresponding device driver or getting one that's open source from TensorFlow in some other setting and using it in our setting. NVIDIA, for example, which supplied us with the Tesla T4 GPU accelerators, they actually provide a standard library with the standard adapters. And so the application should see a very standard looking environment. TensorFlow systems like that are already designed for sharded infrastructures. It may not realize that it's running on the same nodes as the storage and therefore getting the performance benefit. TensorFlow doesn't have an awareness of that in the application. That's also true of Spark and Databricks. However, if our scheduling is done correctly, it was one of the slides I skipped over, we will have placed, have pre-positioned or cached the input values to the model so that the computation and files it normally reads. We have a notion of a dependency set. And when we were given and that again comes from these languages like TensorFlow or Julia, they give you a kind of graphical representation of the application and what it's going to do. It's an approximation, but we schedule based on that. And so with luck, when that data came in from, my example was the photo from the farm, we can actually look at this image and can predict the job that will run. That's easy. But also, where is the best place to run that job so that the needed data will be local, and and then at that point, the expression of the computation really, I had these tiny little black boxes, just had a few lines of code. Often the algorithm looks as small as that, except that if you look closely, you notice that some of the functions being applied are, for example, GPU kernels that might do rather expensive computations like the image classification computations, have inputs which came from other objects, but we happen to have put them in the GPU cache. And so the logic of even those small pieces of code can be quite sophisticated. And with a little bit of luck, that logic ends up not having to do any additional data transfers. We would have done them transparently, but we didn't have to. And we end up with the full benefit of the hardware right at that spot with no delay. So that's the thinking. Now, of course, if we're given very poor quality information about what objects will be referenced by that little black box code, then we're going to have to transfer things from other nodes. But then hopefully the next time around we've cached it and we still get a very high performance. So that's how we go about this.
I do have another question, if you don't mind.
Of course.
Yeah. We know that machine learning algorithms always take a lot of time to train. Is it possible to and the model is contributing a lot of latencies, delays to the entire structure. So is it possible that we train those models offline with some generalized?
Yeah, of course. So the reason that the model, that the code, the hyperparameters in the model were already in the system is that the young woman I showed in that picture probably trained her dirty cow model previously and stored all of that. And now she's built a first-tier application, and when a cow photo comes in, what this particular application does is to run that existing model with its existing hyperparameter input and model parameter input on this photo. And so they come together to give an answer: she's clean or she's too dirty and has to be sent to the cow wash. Yeah, so that's absolutely. Now, the other thing that you might sometimes see and that we support would be what people call few-shot training, where you have a generic model of, say, a cow, and then you specialize it by doing additional training in real time at the edge. So the first time you see this cow, you might train a bit until you learn to recognize her. And then that would create dynamically a new trained model with its hyperparameters and so forth. And then we can store that. And we're given these things with dependency information that tells us that they will tend to be used as a group, and enough additional information to understand what the job that might use those, classification job. And at that point, we can place that grouping in a smart place using optimization. And when it's used in a subsequent classification, with luck, if we're back to the first case where we placed it wisely and the computation starts to occur, everything is right there local.
Thank you for
the
answer.
As I said, it could give thousands of folds reduction in latency to take actions. Because if you look at the current cloud, it's terribly inefficient. They do things like uploading a photo and storing it and replicating it a couple of times in a storage service which guarantees permanent persistence of your picture of clouds over Kenya. Then you run your machine learning code, which internally downloads the images, calculates, says these images are all garbage. You're charged for storing them anyway. And during that whole process, you may have wasted, 10 seconds. Much more in some cases, hours in some cases, because of batching, where they want to accumulate this whole batch, and you have to pay for all of that storage too, which all can go away here. Our data path ideally is image goes straight to the GPU memory, which is where this particular recipe wants it to be. We apply the GPU kernel corresponding to this DNN classifier, or whatever it happens to be. The other objects it needs are there as inputs, and it just computes. A few milliseconds later, we reject the photo because it was all clouds, and we don't bother to store it unless the app. So you can even imagine that one of these triggered actions could be store the photo, or we could have a dialogue. We could say, this is a pretty good picture. Go back and get a high-res picture of the back end of that cow so that we can do a body fat assessment. This is something they would like to do to see whether she's bulking up, which is something cows do when they're becoming ready to go into estrus, when they could be bred. So, you can even get a back and forth that would occur in real time, and that's what we're after. Because if you don't tell the camera quickly that you want that picture of the back of the cow, she's walked past and it's too late to get it.
So can I ask a very simple sort of high what is that, 20,000 foot question? So it's really clear this is necessary for many tasks, high speed machining or traffic, autonomous vehicles or something like that, where you really have to move fast. If you come to slower applications such as agriculture or energy conservation in an organization or something like that, is this going to be something that are there any disadvantages for using this for slower? In other words, why not make this the universal kind of approach to IoT data handling? Or is this, because of its specialization for very high speed, does it have handicaps compared to more traditional ways of doing it where speed is not a problem?
Well, I would say everything has advantages and disadvantages. In settings where batching of large amounts of input, if you think about, say, Google with Google Maps, what they try to do is solve the all parties versions of problems. So, for example, lots of drivers will want to know where restaurants are, so they're going to calculate in one computation all the best answers for all the different places a query could be issued. Later at runtime, they're just going to look up the answer and display it. You're looking for food. You don't happen to like Arby's. They filter that one out and they show you the other options. So that style of batched offload computing that pre-computes an index and then sort of uses it, it's very popular. And I don't see the slightest reason why people would migrate away from it to this. we are getting very high levels of utilization, but the whole point for us is to do much more elaborate triggered sequences of things in real time. And I would say, people who don't need that, why would they go to the trouble of migrating to this? But on the other hand, for the IoT case, there isn't a really good solution. There are lots of products that are coming out in this general area, databases aimed at streamed events. There are hundreds of database products actually for real-time trading on Wall Street. Would those people migrate to this? I don't really know. It's not, I don't know enough about Wall Street computational and analytics work to know if we really would be an ideal data path for those folks. So it's complicated, but I do believe that for the cases we've really studied, where Microsoft has been very helpful, showing, we're also starting to talk to companies like the Canadian Telecom, TELUS is quite interested. We got a call from Siemens the other day. They're very interested for process control. There are a lot of these companies are very frustrated by the inadequacy of edge support. So the 5G people are saying, look, we're building 5G cell towers. They have substantial kind of compute clusters in them called mini clouds. Why can't that be an edge cloud that the telco operators could operate on? And there's a lot of things that you can only do close to the vehicles or to the users. I agree with them. And I think that, so the answer to your question, I could imagine Cascade going down a path where it becomes a part of an open source solution for that world. I'd be very happy about that. I don't imagine it displacing the existing backend systems, which are really very successful in the mode they're normally used. So,
okay, thank you.
And as for, the people who run the ITER fusion reactor, maybe they would look at this and say, yeah, we're still 100 times too slow. It's quite possible. They build custom hardware at every piece of their path. And I don't know how quickly you have to be responsive to adjust the magnets in a fusion reactor so the plasma won't spill out and burn the reactor side. But quite possibly we're too slow for that. I did get a phone call at one point from what appeared to be a military officer in a foreign government worried about hyper fast control of probably, cruise missiles or something. But we told them we didn't want to talk to them. So there are probably cases which we're not even fast enough for. Now, I'm not even sure that's a bad thing.
Yeah.
If you're open source, you're helping everybody.
Thanks.
Other questions? All right, the silence. I think maybe I should just thank everybody and let you get on with your day.
Can I?
Yeah, sure, of course.
Yeah, we talk about microservices. As a student, I took Professor Dimitro's course on 57 on data center computing.
I use slides from it in my course, actually, with her permission.
Great course. And and my question is, can this architecture benefit from the idea of microservices?
Yeah, in fact, we actually think of these things we're building as microservices. In a different kind of context, I might describe Cascade as an infrastructure for creating new cloud microservices under time pressure. And the terminology Christina would probably apply to my work is different than what I'm using here. The community I've been talking to mostly is centered on the fact that they do AI and not very focused on the underlying infrastructure. And I've tried to design this talk around terminology that they do know about, sharding and so forth. The microservices community that Christina deals with is more commonly focused on today's advertising placement infrastructures, or things like when you shop at Facebook or Google, some of their online infrastructures for rapidly showing you other products like this product, rapidly rotating the shoe so you can see the different perspectives on how that shoe would look. Those are all microservices in a pipeline. The deadline that they care about a lot is the 100 millisecond goal of getting the Amazon or the Facebook page rendered in 100 milliseconds. And so what they do is they have the first tier and it spills the work out across a whole bunch of microservices. So that's a similar need, and I think actually would benefit from Cascade. However, I would say that that particular architecture is better supported. Its main flaw relative to what I'm trying to do is they operate with very stale data that's typically very heavily cached. So they take the view that they're running a query, a read-only workload to figure out which ad to show you, but that there's a separate data path for updates that goes to some sort of back-end database. A few hours later, indexes get updated, and then they're caching the data that they're really operating out of. So it's all a read-only type of, so those microservices are read-only out of cache data. We're dealing with the IoT world where the actions you take for the power grid need to be based on a fresh view, a current view of the state of the power grid. You can't control a power grid based on how it looked 20 minutes ago. So now the IoT updates must occur on the actual data in the microservice in real time. And that's not something that those architectures really do. So if you've taken Christina's course, she would not have been looking at that question because it just doesn't arise for those kinds of systems. They have a separate data path that takes the updates to the back end, and much later the consequences become visible. There's a question over here in the window saying that my lecture was very CS oriented and wondering about educational resources for systems engineers. This is a good question, and I don't really have a good answer for you, Felipe. I think that systems engineering is a challenge, right? Because it lives in between areas like computer science and electrical engineering and mechanical, for example, and lives in the middle. All I can say is I'm not an expert on machine learning, but I've been able to learn enough about machine learning to have the dialogue with these people about their needs and be able to offer something that they seem to get excited about. So my advice to you in systems engineering is to say, well, you can take courses audited, not with the purpose of learning the material deeply, but with the purpose of understanding the language and the dialogue, and then say, I'm an expert on this, but I understand what you're trying to do, and I think I can make my infrastructure better for you. Or for example, if systems engineering will very likely be the home of a lot of augmented reality types of use cases. And Flipper said, well, what I'm a specialist in is servicing helicopters very quickly when we're doing firefighting events, and we have heads-up displays and stuff. And the associated language becomes highly specialized, and you just need to know enough about the infrastructures around you to know how to use them efficiently. But no, I can't point you to good resources. I've written books, but these days people don't read books. And I just don't know what to say, except that unfortunately that's a gap. In fact, Randhir Chandra, the chief scientist for Azure, when he visits at Cornell, is constantly asking if we would write a book or some kind of MOOC or something that would be easily accessible and educate 100,000 people about the opportunity here. And I've told him I don't know how to do that. So, sorry.
Yeah, thank you. I'm going through the material that you put in the syllabus in your class and trying to get that overview.
So. You can be the guy in the back of the room who's missing some of the points and getting the others. That's not so bad. Good. I like everything. No, I'm not fooling myself. I don't have much knowledge about how DNNs are configured, but I'm beginning to understand how they talk to the file system and why. That's what I needed to understand.
Yeah, thank you.
That's my advice. Any other questions before we wrap up? I
still have.
You have a long list. Okay.
I'm just so excited to.
I think we should call this the last question, just because we're going to run out of time in the allocated slot here.
Oh yeah. So
ask the last.
Right. Oh, if there's no one else asking, so last question is. I've been also working for Professor Robert Van Rens, so I know he might ask something with regard to the concurrency. How do you manage that?
So I've sort of illustrated that here. I'll answer by going back to this picture we had earlier. So this is a picture which is actually capturing, in some senses, animating the kind of concurrency we really see in Cascade. New objects are being stored into the infrastructure. Computation is trying to query the data that's recently been updated. And we would like a strong consistency guarantee without locking, because locking would slow everything down. And we do that by looking for these consistent cuts, and we do it on the stable portion of the system where the data is not going to change anymore. What makes something unstable is you might not yet have all the data for that time period. Or you may have seen something out of order and you're waiting for the prior event. You might even know that you're waiting for the prior event to reach a given spot. HDFS doesn't track that kind of thing. So the synchronization issue that arises in Cascade is shown on this picture. If you read the Dracho paper, there is a section discussing the way that we do this. It's a form of what's called snapshot isolation. That's the formal model, which gives a guarantee of a consistent cut that corresponds to a serialization ordering on the Paxos atomic updates. The updates inside the shards, these Paxos updates, are basically like a small atomic transactions. They don't actually need any form of locking because they're done using the state machine replication model. So these updates are state machine replication events. The logs are getting appended getting append extends. They stabilize, meaning that there won't be any updates to the past portion of the log. And then we can immediately start to run queries against the stable prefix. And that's what's being shown here, these lambdas. And if one of the lambdas were to try to access data that isn't stable yet by saying, I'd like to look at at 10 o'clock, but at 10 o'clock hasn't quite stabilized, we just delay it at that point. That query pauses until the 10 o'clock data becomes stable. And we have a way to detect stability. So in the Cascade paper, in the Dracho paper, we talk about this algorithm kind of carefully. And Cascade simply uses it. We're going to write a Cascade paper. One of our debates is, do we explain this a second time in a different context? I don't like to write the same paper twice, but at the same time, something has to be self-contained and complete or people can't understand it. Okay, so I think we're going to stop because I know that we're out of time for this slot, but I do want to thank everybody. We would be very happy to have users who see application opportunities. Cascade is still a work in progress. Dracho works, but it's just a C++ library. But within a few months, Cascade will be solid enough that third-party users could really pick this up and start to do things with it and benefit from these kinds of performance levels. And as I said, Weijia someday may commercialize this, but even if he does, I'm committed that anything that my group does will be open source. You can use our stuff and it's not going to be yanked out from under you. And we try to have a very high quality of professionalism for the development. So thank you very, very much. And I hope to be a participant in these lunches from now on, asking all these questions instead.
Thank you.
Thank you.
Okay, well, bye everybody.